Welcome back, everyone, to Fly Vehicle Dynamics. This is lecture 14 in week number 5. Last time we saw how to parameterize the attitude and the attitude rate of a fly vehicle using some parameters. We developed first a general formula for the rotational kinematics, and then we described several ways of parameterize the rotation matrix. We can use sets of minimal parameters, meaning 3 parameters or more than 3. In this case, the sets will be called non-minimal. As we already saw in the beginning of the course, the Euler angles are 3, and they represent, therefore, a set of minimal parameters, whereas the new parameterization that we saw last time is done using the so-called quaternions, which are 4 parameters, beta 0, beta 1, beta 2, and beta 3, and they are defined using other 4 parameters, E1, E2, and E3, which are the components of the unit vector of the Euler's principal axis. Euler's principal axis is a special axis that allows us to go directly from the inertial frame of reference to the body frame of reference by applying a single rotation. And the single rotation is of angle phi. The things that we saw last time was 2 properties of the quaternions. Well, first of all, the norm of the vector beta is 1, or in other words, beta 0 squared plus beta 1 squared plus beta 2 squared plus beta 3 squared is equal to 1. And also, we saw that to avoid redundancies, because we're dealing with a non-minimal set, so we're going to encounter redundancies, which are not as bad as singularities, but nevertheless, we have to deal with them. So we chose beta 0 greater than 0 for all times. Well, I'm going to come back to this statement, and when it comes to actually computing the rotational kinematics, and so the quaternions, we can actually relax this requirement, this beta 0 greater than 0. Before actually going forward with this lecture, I want to point out a couple of things that need to be changed from last lecture. So first of all, when I described the typical parameterization of the rotational matrix RBI, I erroneously described the classical and the modified Rodriguez parameters, a method, as non-minimal parameterization, whereas they're actually minimal because they use only 3 parameters. The other thing, so this is more conceptual, and a practical thing instead was here psi and phi were exchanged. So I inverted the 2. So please correct, or just download the new PDF file with the corrected notes. All right, so going back to today's lecture. Let's continue describing the quaternions and how to use them in order to describe the rotational kinematics. All right, so using what we already saw last time, the definition of the rotation matrix using E1, E2, and E3, and phi, we can write the matrix as follows. Now we want to write the same matrix, but now as a function of our new parameters, the quaternions. So we want to have as entries of these rotation matrix only beta 0, 1, 2, and 3. So we need to pretty much work using the definitions of the quaternions and rearrange these terms and find a new expression for RBI. So before doing that, let's just recall a couple of trigonometric identities. We have that cosine of phi is equal to 1 minus 2 sine squared of phi halves, which is also equal to 2 cosine squared of phi halves minus 1. And then we have this, that sine of phi is equal to 2 times sine times cosine of phi halves and phi halves. So using the definition of the quaternion and these trigonometric identities, I can rewrite the first term of the rotation matrix, so the term 1, 1. And I'm gonna skip the description of the steps. I left them for you to check how we go from one to another. It's not really that important. It can be fun / tedious, depending on you, exercise. So anyway, the first entry, so 1, 1, just in terms of quaternions becomes beta 0 squared plus beta 1 squared minus beta 2 squared minus beta 3 squared. And similarly, for the other entries of the principal diagonal, or the main diagonal of the matrix, we find that R22 is equal to beta 0 squared minus beta 1 squared, but plus beta 2 squared minus beta 3 squared, and a similar thing for the entry 3, 3. Now I'm just gonna show the calculations for the term, let's say it's 1, 2. And what I'm doing is always using the definition of the quaternions and the properties, the trigonometric properties that I listed. So for the entry R12, we find that in terms of the quaternions, that is equal to 2 times beta 1 times beta 2 plus beta 0 times beta 3. And so proceeding in the same way, and you're very welcome to fill in the other entries, you can find all the elements of the matrix. So finally, we have parametrized our rotation matrix that takes us from the inertial frame of reference to the body frame of reference, or in other words, that the rotation that describes the attitude of the vehicle in terms of our quaternions. So you see in here, we only have from beta 0 through beta 3. And also, if you were to compute the same matrix, but for minus beta, so if you were to substitute instead of beta 0 minus beta 0, instead of beta 1 minus beta 1, so on and so forth, you'll see that you'll obtain the very same matrix. In fact, we only have quadratic terms, either terms that are squared, so the minus will just disappear, or a product of two minuses will be a plus. So you're back to the very same matrix, even though your initial argument is minus beta vector instead of beta. So we find that the rotation matrix associated with a set of quaternions that is opposite to the initial one, so RBI of minus beta is exactly equal to RBI of beta. So it means that we have two parameterization for the same attitude, the redundancy that we've already talked about. Okay, so as we saw for the Euler angles, once we have, or if we have the rotation matrix and we want to retrieve the quaternions from the rotation matrix, well, we need to look at the entries of the matrix and find some relationships in order to explicit our parameters. So in this case, for the quaternions, we can use the following. We can have beta 0 as plus or minus 1/2 square root of the trace of RBI plus 1. Recall that the trace of a matrix is the sum of its diagonal terms. Then we can find beta 1 by taking RBI23 minus RBI32 divided by 4 beta 0, where beta 0 is the first term, the first quaternion that we computed. In a similar way, you can find beta 2 and beta 3. Everything's fine, right? Well, not really, because you see now we have in the expressions for beta 1, beta 2, and beta 3, at the denominator, we have beta 0. So what if beta 0 is 0? Well, that would induce a singularity. But the whole purpose of using quaternions was to avoid singularities. And now we've just run into another singularity. And we have an extra parameter. So this doesn't make any sense, does it? Well, we can find a workaround, which is not very difficult, to be honest, that will avoid the singularity for beta 0 that could be potentially equal to 0. So this workaround is called Stanley's method. And the way we get rid of the singularity is the following. So we kind of start from the same expressions for beta 0, beta 1, beta 2, and beta 3, but we take the square. Okay, we square both sides. So now we have beta 0 squared, which is equal to 1 plus the trace of the matrix, everything divided by 4. And then we have beta 1 squared, that is 1 plus 2r. Well, it's a little bit different, actually, the last three expressions, but nevertheless, it's equivalent. Stanley's method can be, it's usually seen using, or it's usually described using these four relationships, so I'm just going to stick with these. So beta 1 squared is equal to 1 plus 2 RBI11 minus the trace of RBI, everything divided by 4, and then you have B2 squared and B3 squared. The convenient thing about these four relationships is that we're only playing with diagonal terms of the rotation matrix. You see, the trace of the matrix involves only R11, R22, and R33. And then for beta 1, beta 2, and beta 3, once again, we have the trace of the matrix, and then RBI11, 22, and 33. So now, what are we going to do? You could just take the square root of all of them and take the positives, right? Well, not really, because let's say that you take the square root of the first term, the first relationship, you'll find beta 0 that is equal to everything on the right-hand side, square root of, which is either plus or minus. So let's say we select plus, but we still have the same problem of sign for the remaining three relationships. So technically, we have 8 combinations. And we know that we don't really have 8 redundancies. We only have 2 sets of quaternions that determine the same attitudes, not 8. So we would make definitely a mistake. It would be just a chance, 1 chance out of 8 to get the right attitude. So in order to avoid this problem, what is done is described in step 2. We select the maximum between beta 0 squared, beta 1 squared, beta 2 squared, and beta 3 squared. Okay? So whichever is the maximum of the 4, and there will be one that is maximum, and obviously that number is not going to be equal to 0, because recall that if we sum up these 4 terms, the 4 squares, their sum is going to be 1. So the maximum of these 4 terms has to be greater than 1. So whichever is the maximum, we take it, we take the square root. So let's say that the maximum is beta 1 squared, then we take the square root with a positive sign. So in this case, it's going to be 1/2 plus 1/2 square root of 1 plus 2 RBI11 minus the trace of RBI. And this is our beta 1. Now, how do we get the remaining 3 quaternions? Well, we're going to use another set of relationships that combine the product of 2 quaternions at a time, for example, beta 0 and beta 1, beta 0 and beta 2, so on and so forth. And so we divide by the quaternion that we've just found. So for example, if continuing with the beta 1 example, we need beta 0, beta 2, and beta 3. So we select of the following, or of these 6 relationships, we're going to select only the ones containing beta 1. So we have the first one, which contains beta 0 and beta 1. Then we have the fourth one containing beta 1 and beta 2. And the fifth one containing beta 1 and beta 3. Now you see that if you take the first relationship and you divide everything by beta 1, and we can do that because beta 1 is guaranteed to be different than 0. So we find beta 0 that will not blow up to infinity. In other words, we're avoiding the singularity. Same thing can be done taking the fourth relationship and getting beta 2, and the fifth for beta 3. Okay, so this is just the example in which beta 1 squared was the maximum of the 4 terms. If the maximum was another one, you would repeat, but choosing different combinations of the 6 relationships. Now, if we want to guarantee the fact that beta 0 is greater than 0, then we just have to check whatever we found in step number 3. So if beta 0 is already greater than 0, then that's it. You have already beta 0, 1, 2, and 3, and those are your quaternions, and you're done. Instead, if you find that you get a beta 0 that is less than 0, then what you do is simply flip the signs. And so your new beta 0 will be the old beta 0, but with the minus. So it will become a positive number. And we don't really care for beta 1, beta 2, and beta 3. They don't have to be positive or all negative. So this is Stanley's method. And by following these 4 steps, we've got rid of all possible singularities, and we find a set of quaternions starting from our rotation matrix, okay? So the whole objective of Stanley's method is to determine a set of quaternions based on the rotation matrix. So if we have the rotation matrix, we want to find the quaternions, well, we have to use Stanley's method. If instead we already have the quaternions, we just plug them in equation 1, and we find the rotation matrix. So no need to go through Stanley's method, of course. All right, now the lengthy part, at least for me to write, but I'm gonna go very fast, hopefully. So the objective here is to, starting from the general equations for the rotational kinematics that we developed during last lecture, and we have RBI as defined above, equation 1 over here, okay? And of course, we like our angular velocity expressed in body coordinates. And in lecture 9, we said that we're going to call the components as in P, with P, Q, and R. So of course here R is the component and it's not a rotation matrix. So I think it's going to be fairly easy to distinguish the two. As a matter of fact, I think I kept the components of the angular velocity in blue, so there shouldn't be any problem telling the components of the angular velocity from the rotation matrix. Anyhow, what we want to do is to rewrite the general equations for the rotational kinematics in terms of quaternions. And we start by, actually, there's a little bit of a trick here, but I'm going to describe it anyway. So you take the time derivative of the three elements of the principal diagonal of RBI. So you're going to find RBI prime 1, 1, RBI prime 2, 2, and RBI prime 3, 3. So you have to take the time derivative of the components of the principal diagonal of the rotation matrix. And so you find, for example, for R dot 1, 1, 2 B0 B0 dot plus 2 B1 beta 0 beta dot plus 2 beta 1 beta 1 dot, and so on and so forth. And this can be repeated for the other two expressions. Now, if we go on the right-hand side of the expressions for the rotational kinematics, and we use the skew matrix for the angular velocity, and then multiply by the rotation matrix R, then we find a new matrix. And here, once again, we're considering only the diagonal terms. So we're going to equate the left-hand side, which is given by these three. So this is the left-hand side of the rotational kinematics with the right-hand side over here. So we have three equations, but we need a fourth one. So the fourth equation that I'm using is this: beta 0 dot plus beta 1 dot plus beta 2 dot plus beta 3 dot, which comes from comes from the fact that we are differentiating beta 0 squared plus beta 1 squared plus beta 2 squared plus beta 3 squared, and that expression is equal to 1, correct? So the time derivative of this expression has to be the time derivative of 1, which is a constant, therefore it's 0. So here we go, and we have the fourth relationship. Now, applying a little bit of algebra, and you're welcome once again to do it yourself. I really think you're not going to do it, but that's why I did it for you. We find an expression for the beta 0, 1, and 2, and 3 dots as a function of everything else that is a function of just quaternions, beta 0 through beta 3. And of course, our angular velocity components. Now, how do we explicit the beta dot vector? Well, we have to take the inverse of this matrix, or just starting from the first row, we see that 4 beta 0 times beta 0 dot is equal to minus 4 beta 0 beta 1 p minus 4 beta 0 beta 2 q minus 4 beta 0 beta 3 r. And so we actually have an expression for beta 0 dot. over here, you can do a similar thing, cascading to the second, third, and fourth of these linear equations, and you find not only the explicit expression for beta 0 dot, but also for beta 2 dot, beta 1 dot, and beta 3 dot. And if we want to write it down in matrix form, we have that the vector containing the time derivatives of the quaternions, so we have beta dot is equal to 1/2, and then we have this 4×3 matrix, which now I'm going to call it capital B of beta, because it's only a function of the 4 quaternions, times the angular velocity. Angular velocity expressed in the body coordinates. All right, so we're actually done. We found the equations that describe the rotational kinematics using the quaternions as our parameters. And that's what we were looking for. Now, there's a little thing here to consider. And, when you want to find the quaternions as a function of time, you have to integrate these equations. But if you integrate them numerically, the condition beta 0 squared plus beta 1 squared plus beta 2 squared plus beta 3 squared equal 1 might not always be satisfied. So every time you integrate, you call your integrator, you have to renormalize the quaternions when you input your initial conditions, or you have to make your tolerances a little bit stricter. And so, speaking about computation, let's see how we can actually use our rotational kinematics, expressed in terms of quaternions, and how to implement that. Okay, so usually the initial attitude is much easier to express it in terms of Euler angles, because they have a physical meaning, and it's easy to understand or to visualize even what a roll angle is, what a pitch angle is, and what a yaw angle is. So usually you're going to find your initial conditions in terms of Euler angles. So here we have our initial condition vectors with our initial yaw angle, our initial pitch angle, and our initial roll angle. Now, the first thing we want to do is to transform the parameters, or to feed the parameters into our rotation matrix, or, well, I should say we should build our rotation matrix using these parameters. And of course, here it's a rotation matrix for the initial conditions, and that is our usual way, depending on our rotation sequence. If we use the 3-2-1 rotation sequence, that we're going to find RBI 0 as the product of R1 of phi 0 times R2 of theta 0 times R3 of psi 0. Okay, now we have to get rid of the Euler angles, because when we develop, or if we use the kinematic rotational equations using the Euler angles, well, we find the problem with 1 over cosine of theta, so the singularity. So let's transfer everything to quaternions. How do we do that? Well, we find beta 0, so the initial set of quaternions, or the quaternions initial conditions, applying Stanley's algorithm that I just described. And now if you pair the initial conditions in terms of quaternions with the quaternions kinematics, and I haven't really described them, but you can see that there's no singularity. Nothing is at the denominator. Nothing will go to infinity if any of the quaternions go to 0 or to a particular value. Everything's fine, and they also look linear. It's in fact a bilinear system. So it's nice, it looks nice in terms of linearity and in terms of not having singularities. So combining the kinematics with the initial condition, we find our quaternions as a function of time. Now, it is wise to normalize the quaternions with their norm in order to enforce the condition beta 0 squared plus beta 1 squared plus beta 2 squared plus beta 3 squared equal to 1. And again, this is done purely from a computational perspective. If you were to solve these equations analytically, you wouldn't have to do this step. All right, so now you have a set of quaternions at any given time t. So you can use them using equation 1 to find your rotation matrix. You just plug in the values of beta 0 through beta 3, and you find your rotation matrix at time t. Now, what if we want to go back to our Euler angles? Well, the rotation matrix is the same whether we express it in terms of any set of parameters. So RBI at t, whether we express it with quaternions, well, now we only have numbers actually. So that is equal to RBI expressed in terms of Euler angles. So now using the relationships that I showed you earlier that I made a little mistake, we can go from the rotation matrix RBI to the actual values of the Euler angles at time t. Now, if we want to use this new set of Euler angles as a new initial condition, let's say this is just an integration step and we want to reintegrate again, then we can use the set of Euler angles that we just found as our new initial condition and repeat the cycle. So as you see here, I've never really enforced the beta 0 greater than 0. And that is totally fine because whether it is greater than 0 or less than 0, well, we're still going to find just one set of quaternions, and whether they have a sign or all of them have the opposite sign, they all refer to the same attitude. So it's totally fine. Computational wise, you can enforce this or not. It's up to you. I don't, because I like to see quaternions that are smooth functions. So you really don't have to do that. The only time we actually imposed the beta 0 greater than 0 condition was in the Stanley's algorithm. So over here. So when you really initialize your quaternions. All right, so this is all for today. And so this is going to be part of the midterm. I am going to make some announcement describing a little bit more about the rules and how the midterm is going to be like. So wait for some announcement later today. And I haven't assigned homework because there's not going to be homework due this week. I will post later today some extra problems so you can solve in preparation for the midterm. I already invite you to look back at the homework from 1 to 3 and solve also the problems that were not due, and then take a look at the quizzes. Okay, very important that you understand, and just try to understand everything that you read. Okay, if there's something that you don't understand, feel free to ask. It's better to ask before the midterm than after. All right, this is everything, and I'll see you next time. Oh, on Wednesday, I'm gonna go live. So we're gonna have a live lecture at 10:50, and I'm going to answer any questions that you might have. So it's gonna be a live Q&A session. And then, of course, on Friday, we're gonna have our midterm. All right, take care. Bye-bye.